equals all over I do this and take this here. Here. Okay, let's do the first one. We already should have learned about electron configuration. So please, using a handy dandy periodic table, you can use this one. We're talking about iron, which is right here. Someone give me the electron configuration of iron.
1s2, 2s2. 1s2, 2s2, 2s6, 3s2, 3p6, 4, 3.
Do you want the simplified notation? What's it called?
Noble gas configuration.
Is that
So what answer does that correspond to?
46. Oh, yeah.
Don't worry, since the options don't require it,
A.
then you can't use noble gas.
Okay. That's not right.
Yeah,
A is not right.
the
2s2, 6, 3s2, 3p6, 3,
5?
So the thing is, when you write it, it doesn't matter what order you put it in.
As long as the ends are the same as you go across. Okay.
Which is why D is the right answer. And like I said, you could have wrote the 42 or the 3d6 and it would have been. You could have wrote the 42 first and then the 3d6 and it would still be the same thing. That doesn't matter.
The case when writing that stuff, but like the case where you do like 3d6 before 4s2 is when you're doing Alphaus principle, you need to write out like the whole electron diagrams, like the orbitals and the upspin and the downspin of the electrons. You'd make sure to fill the 3d orbital before you fill the 4s. That's lower in energy.
That is,
Wait, but then why do we? The same question last time. Why do we fill the 4s2 before we fill the 3d?
Why do you fill the 4s?
Or why do you fill the 4s before you fill the 3d?
Because 3d orbital is higher in energy.
3d.
Oh,
4s. Okay.
but look at like molybdenum and chromium. A
The
half-filled
exceptions.
D subshell is more stable than a 4s.
So you take one of them, move it over. Same thing with like copper, silver.
And that's honestly probably why they wrote it first here, because the D subshell is more than half filled, so it's already lower in energy than the 4s subshell. So again, like up here on the periodic table, we know chromium and molybdenum are exceptions to the electron configuration, right? Because instead of having it be 3d4, you end up taking one of the s electrons to make it 3d5, because a half-filled D subshell is more stable than a fully filled 4s subshell. All right. That's why you can do it like that.
Is tungsten also not an exception?
Tungsten doesn't follow the trend because it has that F subshell too. Like there are exceptions for that too, but we won't get into the second one.
Oh, what kind of, what kind of heat is them? The Ocam?
No, not okay.
We don't care about
It's-
electron.
Yankum too?
Nope. It's like higher levels than that, probably like PChem or something.
Pecan?
Yeah.
PChem 1, PChem 2, something.
Or like inorganic chemistry.
Inorganic? Oh, shoot.
Okay, so let's go ahead. Let's go do these. These look like good. 24. You want to do 24?
Does it change?
24?
What do you mean?
Like,
Yeah, did you say you just move it up one energy level?
So what do we think?
So. Did you say?
It's not.
I put E.
E.
Oh, yeah, since it's originally 2p2, we just removed the 3s.
I'm pretty sure the answer, wait, you said you put E?
Yeah.
Mhm. And again, because what is the outer valence electron configuration for carbon? It should be 2s 2 and then 2p2, right?
That's outer.
The valence.
Oh,
So
Yeah,
the
there's a 1s2 in there too, but we're
1s2.
supposed like helium.
how do you know which? The outer versus.
Well, it's because it's the valence electron, so the one
Oh.
that's not filled up yet all the way. So even if it was like neon, it would have still two p six, but those would still be considered their valence electrons. Even though neon valence electrons are electrons that are involved in bonding, and neon will typically not be found in.
It's a noble gas, octave.
Exactly. All right, so for an excited electron in a carbon atom, you have to have something that gets to a higher energy level. So a two p electron will jump to either most likely a 3s subshell, or in some cases, depending on the energy, it could be even a 3p subshell. But most of the times we'll see a jump to the 3s subshell. So in this case, we have the 1s2, 2s2, which is right. And we have one electron that comes from the second or the 2p subshell and jumps into the 3s subshell. And that is when you have an excited electron in a carbon atom. And why is it, how do we know it's a carbon atom? Because this is showing the amount. If you look at the valence electrons, it would be 2 for the 2s subshell, 1 for the 2p subshell, and then 1 is still out here. That was the excited one. So it'd be 4 valence electrons in that case. Makes sense, Audie? Okay. Let's do. So go ahead and do number 30. If we learned about this yesterday and today. So this might go against everything we're gonna learn. Want to do? Sure. So yeah, I thought you were.
Why is this a bad situation?
Don't worry about it, Rich. You already know.
All right, raise your hands if you all have answers. All right, with pride,
Higher, guys, come on. There we go.
be higher with pride.
Audie, is that high with pride? There we go. Okay,
All right, we'll go.
on 3, you want to explain it or you want them to see if they're right?
All right, Maria, tell me what the correct answer is.
It's T.
Why is it?
So when you move down a group, you're adding energy levels, so that makes it bigger, and then when you move from left to right, you are increasing the nuclear charge.
So it's what to the valence, it's pulling on them.
It's pulling on the valence electrons.
Got your money up. Correct answer is in fact,
Increasing.
Yeah, because the nuclear charge, as you move across from left to right, you're increasing the amount of protons in the nucleus. Just
Yeah,
that's
oh,
the
yeah.
atomic number, right? So because you're increasing the amount of protons in the nucleus, it's able to increase the pull on the valence electron.
If it increases the pull on the valence electron, it makes it smaller.
Exactly, so
Oh,
radius would
from
be-
right to left.
No, from left to right, radius decreases.
Yeah,
Okay, so
because there are more protons as you go to the right, right? If there are more protons.
yeah.
Pull on the electrons.
Yeah.
Yeah, I got the word.
so from it increases as you go right to left, or you could say it decreases as you go from left to right.
Yeah.
Makes sense? Yeah. Perfect. Let's see, do the next one, 31.
All right, number 31. The atomic radius of main group elements generally increase down a group because.
I think you're cutting off part of the last. There you go.
That is in fact what I thought it was.
That isn't that what you thought it was? Yes. There's a little question on that. Tap it real good. In order to change to the area. What are the top scholars thinking right here? Oh, you're still thinking? You got an answer, Maria?
Yes.
Well, give her the top scholar.
Do that. Yeah.
Hold on.
Oh, you mean question 31?
You have an answer?
Yeah, I did it, and it was right.
You got it?
Yeah, right.
Why is it not,
Oh.
why is it not C?
Um,
Speak loud, proud.
Technically, because you're adding more protons, so it's not that the effective nuclear charge decreases, because there's more protons, technically it does increase. But because of there's more orbitals, that's why the atomic radius still increases, right?
Mm.
Yes,
Well, energy levels, right?
yeah,
Because the principal quantum number is the n value, which talks about the energy level. As the n value increases, you increase the amount of, what did we say?
energy levels.
Energy levels. Those energy levels have a bunch of electrons, and electrons what to each other?
Repel.
They repel each other. Meaning, with the word that begins with the S and then the H. And then
S H.
it ends in yielding.
Shielding.
There we go. That
No.
that increases, you increase the number of electrons, right? So what's the answer, Rich?
I think the answer, in fact, to this question is B. Because the principal quantum number corresponds to n, and then when n gets larger, right, the amount of orbitals, energy levels, right, electron shells, that's what I call them, electron shells, you have increase. And because of that, because electrons want to be far apart from each other, they'll repel, and your atom size will get.
Exactly. Does that make sense to everyone on Zoom? Yes, in the chat, right now, 10 seconds. Thank you, Alex. Thank you very much. Huh, interesting. Only 2 people are active today? Oh, thanks, Ashley. Everyone, okay, ready? Let's go down to this next highlighted one.
All right. Which of the following has the smallest radius? You are free to use a periodic table. In fact, I don't think you can do this without a periodic table. Unless you're like me and you memorize.
Unless you're like me and Rich and you memorized it. When you were 4. And there's a video on YouTube of you singing the entire periodic song.
There is.
He may or not have found other information about you.
I think I already shared my findings.
No, the other people.
Oh, that piece of information. Oh, this- There's a certain individual
Oh, you're
out there.
I saw him this morning.
Alex reckon he has an answer. Rich.
Does anybody else reckon they have an answer?
Anybody else reckoning?
I reckon I have an answer too.
All right, how about on 3? We're all gonna say the answer. Tomer, are you ready? All right, 1, 2, 3. D. Bro, what's your domino effect?
One person goes D, the other person goes D, the other person goes D. What is this?
Okay, wait, go ahead, Rich.
All right, so that's what's.
Yeah.
All right, so
There's a periodic table, you scroll up.
if you scroll up to your periodic table. Now I gotta scroll back here.
Find the
So which of the following has the smallest radius?
phosphorus,
So we got
sodium.
phosphorus, sodium, bromine, chlorine, and iron. So that's phosphorus, sodium, chlorine.
No, chlorine, bromine, iron.
All right, so we have these 5 elements, right, that I've highlighted, not highlighted, underlined.
You can highlight them.
I can't.
Phosphorus, sodium, bromine, chlorine.
Phosphorus, sodium, chlorine. All right. So what's the trend we know for atomic radius? To the left and down, exactly. So for the smallest atomic radius, right? It should make sense that it should be opposite that trend. Because if atomic radius increases down to the left, that should make sense that our smallest atomic radius should be up and to the right. So which of the following elements is the most up and to the right? Exactly. So that is why chlorine has the smallest atomic radius. That is your answer. Which of these would have the largest atomic radius?
Sodium, iron, no, sodium.
This is where it gets a little tricky, but I'm pretty sure I would say sodium.
So which one trumps the other one?
Well, I mean, because like, look at how far iron is over. Like, that's a lot more pull from the electron, like the effective nuclear charge
So sodium would have a higher atomic radius.
than iron, yeah. Because I remember teaching this last semester, and someone asked me about magnesium and scandium. And I told them, it turned out like scandium was smaller than magnesium. But yeah, let's see. So I'm pretty sure like as you move across, like, okay, well, find the effective nuclear charge for sodium. It would be 26 minus the amount of inner electron, which would be 1, 2, 4,
So
6.
26 minus 10.
Yeah,
So that's 16.
wait, 26 minus 10.
Wait, what's 26?
It's the atomic number
Iron.
The atomic number, yeah.
minus the amount of inner electrons, which I think it goes all the way to argon.
26 minus
18.
18. Wait, this is 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8 goes with 26 minus 18.
How do
That's sodium, it's 11 minus 10. So it's 5.
So 11 minus 10, yes, and then for iron, you said 26 minus 18.
Yeah.
Is 8, yeah. So iron has a greater effective nuclear charge. So radius increases in size to the left and up. No, Kristen, radius is gonna decrease as you go from left to right. And then it's gonna increase as you go down.
Okay, I'm so sorry. Repeat that one more time.
So as you go from left to right on the periodic table, radius is gonna decrease because of as you increase the atomic number, you're increasing the effective nuclear charge on the valence electrons, so it's gonna pull that in more. Effectively decreasing the radius as you go left to right on the periodic table. As you go down a group, you're gonna increase atomic radius because going down the periodic table, you're increasing an energy level, right? And those energy levels have a lot of electrons. So the more core electrons you have, the more shielding that happens, and the more shielding means a larger radius.
Okay, so radius increases as you go down, but it decreases when you go to the right.
Exactly.
Okay,
So with that, what would be the smallest element on the periodic table?
okay, well, up and then, so like fluorine, not fluorine, right? Or helium, maybe?
Helium, yeah, exactly.
Because fluorine, although it's really far to the right and up, you still have helium that has it's only in the first energy level, so only has that first 1s subshell. And then it has an effective nuclear charge of like, well, I guess 2 minus, there's no inner electrons, so it has a pretty high effective nuclear charge. So it's gonna be smaller than fluorine just based on the fact that fluorine has an additional energy level full of electrons.
Okay, that makes sense.
And what would be the largest element to that degree?
FR, right?
Oh, yeah, exactly.
Okay. Francium, okay.
Right, does that make sense?
That does, thanks.
Right, sounds good. Okay, so to answer the question, which of the following has the smallest radius, the answer is. All right, 34. Which of the following atoms has the largest radius? And your options are cobalt, strontium, iodine, calcium, barium. So
Calcium, barium.
cobalt,
Barium.
strontium,
Barium.
iodine, calcium.
Pretty low.
It's its biggest.
So that's pretty low. Is that the right ones? Calcium, barium, yeah. All right. The ones highlighted in red are your options, not highlighted, underlined.
Oh,
He knows everything.
Bill, can you unlock your computer?
oh my. Yeah. You don't have that Face ID?
You don't have a whole keyboard underneath.
Oh, keyboard under one.
There's a whole new keyboard for Mac. I was type out other stuff.
Okay. so-
Anyways, back to the point. Raise your hands if you all have answers.
All right, I say we let someone on Zoom explain it. Anyone on Zoom want to volunteer to speak and explain which one it is and why? Kristen, how about you help me out? I'm sorry to do this to you.
Man, you didn't have to choose me. So I chose BA, barium has the largest. But I'm not too confident in the answer because I know the radius increases when you go down. And I'm still shaky if the radius increases when you go to the right. I know you just told me this, but it's still like taking a second to process. So
So you said the radius increases as you go to the right?
that's what I thought, but then I'm not too sure. I thought it was, I don't know. I get my lefts and rights confused, and so it takes me a
Well,
second to get.
Well, let me say this. As you go to the right, so this way. So
Yeah.
this arrow, what are there more of? Are there more protons in the nucleus?
Yeah, there's more protons.
If there's more protons, right, they'd want to attract the electrons a lot closer, right?
Yes. Uh-huh.
They attract the electrons a lot closer. That means the electrons, right, would be closer to the nucleus.
Right. Oh, so it's smaller.
Yeah, exactly. That's what I was
Okay.
saying.
Okay, yeah, so then, yeah, my answer of barium is still correct because if you go to the left, they're bigger.
Yeah.
And if you go down, it's bigger. Okay. Okay. But yeah,
Good
so I got E. Okay.
Yeah, so it's increasing to the left, not to the right. That's basically the main point, what I was trying to say.
Okay.
If anything,
No, yeah,
just
that makes sense.
remember that helium is the smallest element. So you realize that it has to decrease as you go from left to right, and it must increase, or it must decrease as you go up in order for
Yeah.
helium.
Yeah, exactly. That's why I was like, I know what I was thinking with it going to the right was wrong because I know francium's is the largest.
Yeah.
It's kind of like the opposite of electronegativity. That's the way I'm thinking about it.
It's exactly the opposite of electronegativity, and most of the periodic trends are the complete opposite of atomic radius. So like
Okay.
electron affinity, electronegativity, ionization energy, they're actually all the opposite of atomic radius.
Oh, okay. That'll probably help me a lot more just so, because I know electronegativity pretty well. And okay. Cool. Thank you.
Of course. Right, so to answer the question. Okay, the largest radius, yeah, the correct answer is in fact E, barium. And does that make sense to you all as to why it is barium?
Yeah.
Really easy. Give her the possible.
Right, sounds fantastic.
All right.
Let's do. Question 35. Consider the following electron configurations to answer the question. And these are all. All right, just to make sure we're on the same wavelength here, no pun intended. So. Just to make sure we're all on the same sort of page. What are all the elements that correspond to these electron configurations?
Oh, I wrote it down. Rubidium,
Rubidium for the first one,
yes.
right?
Chlorine,
Chlorine,
selenium,
selenium,
argon,
argon,
potassium.
potassium.
This guy has his money up for sure.
All right. So the electron configuration of the atom that is expected to have the lowest first ionization energy is what?
You're gonna use paper.
Isn't it the first one?
And like I just said, ionization energy trend is opposite of atomic radius.
So it goes up to the right, but there are certain exceptions. to this trend.
Oh, there are certain exceptions, and you learned them yesterday.
With ionization energy,
Yes,
we did.
yes.
Hey, Maria, what are the exceptions to ionization?
Oh,
No,
so between group 2 and 3. Group 3 has a lower ionization energy, and then between group 15 and 16, 16 has a lower ionization energy.
Like, so 2 is greater than 3, 5 is greater than 6. I call it 5.
So those are the exceptions that we need to know.
Could you repeat the exceptions one more time?
Yeah, so for elements, right, group 2 elements are higher in ionization energy than group 3. And group 5 elements are higher in ionization energy than group 6.
And this only goes from. for
Periods
five-
1 through.
Yeah.
This is for periods 1 through 4, so like the first 4 rows of the periodic table. So these 4 rows right here.
Okay, thank you.
All right, and the group twos are
So when you
this
subtract.
one, and then group 3 is this one, not the transition levels. And then 5 and 6.
And then
I
you
should don't go down.
I was sitting down in this, I was sitting down.
All right, so those are the ones that I highlighted in that blue color are the exceptions, and it's, again, like Rich said, group 2 is greater than group 3. And then group 5 is greater than group 6, and want to explain to them, Rich, why? I'm not sure if Dr. Sadeghi has gone over that yet.
All right, let's look at it this way. So we have beryllium, right? What's the electron configuration of beryllium?
1s2, 2s2.
All right, so it'll be 1s2, 2s2. I'll draw it in the boxes. So the little electron spin diagrams. I forgot what they're called. I think they're just called electron diagrams, up, down, down. Beryllium would look something like that, right?
Yeah.
What about for boron?
1s2, 2s2.
1s2, 2s2.
Yeah.
Right. So the thing you do, right, is do you take electrons from the paired orbitals or the unpaired? Take electrons from the unpaired ones.
Yes. It's easier to rip away, right? No, wait, no, no. Yeah?
Oh, what you're saying makes sense.
I'm gonna go into the empty space. Did this wait till? All right. Okay, so for group 5s, what did he say? We're gonna use beryllium. Or no, group 5, group 2. And we're gonna use beryllium. And that has we're gonna look at their electron configuration. So it's, this is their 1s, and then we have a 2s, which is completely filled. Now, if we look at group 3, main group 3, it's let's look at boron. So it's boron, and we have the 1s filled as well. And then 2s is filled as well. And the 2p subshell has 3 orbitals, right? And there's only 1 in that one for the main group, group 3, the main group. So in order for okay, I'm gonna use something from organic chemistry. Okay, so the total energy of an atom is related to the orbitals at which electrons are filled. So only filled orbitals contribute to the overall energy of an atom. Therefore, this boron, because it has all these 3 orbitals that are currently open and willing to take in electrons, it's higher in energy than beryllium. So what it actually happens is that this electron, it kind of wants to lose this electron more willingly than beryllium because it's higher in energy, and things that are higher in energy are not more stable, they're actually less stable.
Oh, there's no base.
And so it's gonna actually have a lower ionization energy than beryllium, the first ionization energy, because it wants to lose it.
Wait, so that lone electron has a lower ionization energy?
Yeah, so it's gonna take less, it's gonna take less energy to remove it from the boron atom than than it will to remove one of these electrons from the beryllium. And it's because these two electrons they're paired up and the orbital the subshell is completely filled, so it's absolutely like really stable. But whereas you have this, the whole 2p subshell is open, but only one electron is occupying it. So what I like to say is like, why buy such a big mansion if it costs so much money, or so much time to go dust the entire place on the weekend? If you can just buy a small little house and go about your life and have an easy time on the weekend cleaning it up, Well, not everyone is rich enough to buy a big house and hire a maid to go in and pay a salary.
Because he can.
Audie, do you have a big house? Audie, share your address right now.
Yes, you do. Why are you lying?
Okay, anyways, so again, Audie. Okay, so again, it's very energy costly to open up this entire subshell just for one electron. So it's more willing to lose this electron, which is why it has a lower first ionization energy than group 2 elements. And again, for that's for periods 1 through 4. But there is no group 2 period 1. Yeah.
So when we get to one of the others, they have to tell us that if there's 2 of them, they can tell each other, right? So you know, an electron. Why does it not apply in this case?
Because this is a completely filled subshell.
Oh, so
Whereas
that's only-
and I'll get to that right now. So group 5. It would be nitrogen. No, it doesn't. Because they're two different things. One is you have a filled orbital. The other one is you have a completely filled subshell. Subshells contain orbitals. So.
Power of an element to attract.
Okay, yeah.
And then nitrogen has the 2p, which has 3 orbitals and then 5 valence electrons. Yes. Oh wait, no, we should be comparing. It should be.
So you have.
Yes, carbon.
Yeah.
Okay. Wait, no, because 1, 2, 3, 4, 5, 6. Okay, so group 5 nitrogen look like that. It has 5 valent electrons, 1, 2 here, and then 3 here. So that would be nitrogen. Group 6. Oxygen, and that would have your 1s, 2s, and then 2p. 1, 2, 3 of those. So that's filled. That's filled. Thank you. All right. So this orbital, this entire subshell is not completely filled. We can agree on that, because it can still fit 2 more electrons. So with it not being filled, it's not completely as stable as you would say like a 2s subshell that's filled, or a 1s subshell that's completely filled. So this electron here is actually easier to remove because the 2p subshell is not full, so it's not complete, it's not as stable. And 2, it's also, the electrons are repelling each other, so they don't want to be together. So this electron is more willing to be lost by an oxygen atom. In terms of ionization energy, it's more willing to go away. Although that's not exactly what we see, because oxygen does happen to be one of the more electronegative atoms. It just means that when they measure this stuff, it happens that it just so happens that this electron is easier to hook off than one of these electrons. All right. Does it make sense though, Maria?
Yes.
Because this isn't a complete filled subshell. You agree on that? There's still 2 orbitals that can fit in 1 electron each, right?
Yeah.
So, but once it's filled, then you have noble gas configuration, and then it's happy. So then it doesn't want to do anything at that point. Filled subshells are very stable. Something that's half filled is still more stable than something like this, because you have this electron pair repelling, but it's still relatively unstable compared to a completely filled subshell. A completely filled subshell would look something like neon, where you would have your 2p completely filled.
Is that considered noble gas configuration? or no?
2s2?
Yeah, like if you just
No.
stop it.
No, because the 2s, the second energy level can fit in a total of 8 electrons.
Oh, yeah, because you have the key.
You have the p and the s. While the 2s subshell is completely filled, the s orbital, the s subshell is not being occupied by any electrons, but it still kind of exists. Because the second energy level. Okay, any questions on these exceptions? And again, 2 has a greater ionization energy, so ionization energy is going to increase as you go up. Here, from 3 to 2, and then same thing with 6. I always like to just say that 2 is greater than 3, 5 is greater than 6.
Okay, real quick, just because it was a little difficult to hear you at some points, but so essentially, since the group, like since they're paired in group 6, it's like they want to be removed.
So it's not that it wants to be removed, it's that it's easier to be removed than one of these electrons, because each of these electrons are in their own orbital. So there's no repelling forces. But once you double it up, it doesn't want to, the repulsive forces between the electrons make it unstable, meaning it's easier to remove. It's not that it wants to be removed, it's easier to remove it. Because remember, electrons repel each other. So 2 electrons repelling each other is more unstable than just a single electron occupying its own space. It's kind of like having a roommate, you know, you don't really get along with them. Sometimes y'all are just in each other's space. And so it's easier to get rid of them by just getting rid of them. And however way you decide to get rid of your roommate. Keep that to yourself. I don't want to know how you get rid of your roommate. Let's hear the Justin Bieber analogy.
Oh, my God. No,
I mean, you've heard like 2/3.
Okay,
wait, I never heard.
all right, so let's go further down here. All right, so with that, what's the answer to number 35? Is Dylan projected? Let's just say it's up to interpretation. Okay, what's the answer to number 35? Rubidium. Rubidium.
Wait,
Oh, yeah, no.
wait.
So basically, if Dr. Arnold would give us a question, he wouldn't give us the ionization energy like that.
No, we're looking for the lowest first ionization. We just said that it increases as you go left to right and decreases as you go down.
So that's like. Right thing, that's what.
You can't tell that easily. Ah, okay.
All right. They are.
It is okay.
Yeah, we can tell.
That's all right.
Oh.
We know what you guys. Okay, what did we get for our answer here, guys?
Yeah.
Why is 2 chlorine?
Well, because Tomer told us.
Oh, it's.
I trusted Tomer, and this is what happened.
Oh, wait, 3P5.
Wait, it is chlorine. It is chlorine.
Sorry.
Why are you gaslighting my guy?
I already have issues with the rows.
Honestly, give him the top scholarship, right? Okay. Yeah, it's paid to go to school. I'll stop talking because it's already important.
Yeah, you wish you were the honor college, right? Get Aguilar.
I did get Aguilar for OCAP, didn't I? No, I don't hate a win. Okay.
Thank you. That's what I'm deciding.
Okay, so someone tell me the answer, please. I've asked
It's
for.
A.
Okay,
Why were we?
you were second guessing.
Me, I said rubidium. They said wait.
Okay, the answer is A, because look, let's go to the periodic table. As we go from right to left, we're gonna decrease ionization energy, and as we go down the periodic table, we're gonna decrease ionization energy as well. So we're looking for something that's left and very far down. Out of those elements that were listed, rubidium is the only one that, the rubidium is the one that has the lowest ionization, because it's all the way over here on the left, and it's pretty far down. Everything else is a little bit further out. Does that make sense, to everyone?
You're right.
Yeah. Okay. The electron configuration of atom that is expected to have the highest first ionization energy is what?
So ionization and electronegativity follow the same trend, right?
Yes.
Is that why when
Chlorine.
chlorine is with oxygen just has that's like one of the exceptions for oxygen's oxidation number? Because in fluorine, is that why?
Yeah, that bond's probably crying out in pain because both of them are really electronegative. So it probably like, both of them would be pulling on the electrons really closely.
Nah, fluorine's still gonna pull out more.
Yeah, it is still gonna pull on.
So
The
is that
oxygen
why-
is also pretty electronegative,
Yeah, but fluorine's gonna pull out the harder.
but it is.
Oh,
Is that why oxygen is +1 in that situation? Yeah.
it's a +2 in that situation.
Yeah, because it'd be slightly, it'd be slightly electron deficient because the fluorine would be
Because
pulling.
the only time you see oxygen bonded to fluorine is in OF2.
Oh, okay.
Right?
Then-
OF2. So each fluorine has a -1 charge. And a +2.
So, okay, that makes.
Okay, answer to number 36. 3, 2, 1.
B.
I got D.
Kristen, you're right. Thank you.
Cool. Thanks.
Good job, Kristen. I'm gonna start including you. I'm sorry. I'm kind of leaving you out.
No, you're good. It's okay.
Okay, perfect. So B is the answer again. So we're looking, if it's asking the highest first energy, ionization energy, we're gonna go, we want something that's up and to the right. So out of these 5 here, chlorine is gonna be up and to the right the most. As we see on the periodic table. If
Wait, it's not
selenium-
argon?
Oh,
I said D.
is that D?
Yeah, because argon is like the furthest to the right.
Yeah, no, yeah, you're right. The answer is, I thought I heard people say B. I didn't,
It's wrong.
I said D.
I know argon is.
yeah, it's argon. You're right, Kristen. Thank you for catching that.
No problem.
Isn't that the alpha?
Okay.
Where beta is, so why are you using the hydrogens off of the floor?
But this
Okay.
also beta.
So of the following, here, how about this? I'm gonna go ahead and copy this part. Bring it up to this thing here. And I'm gonna paste that right here. And we're not gonna care about the F subshell because those don't matter. 1, 2, 3, 4. So go ahead and answer using the periodic table on page.
But.
Oh,
Let's see, all the exceptions.
Sorry, I know.
Here's the rows. I don't know what it is. Just, yeah, just call them those. I learned those periods. That's what I'm saying.
Oh, sorry, I was erasing the period.
It's not really true, but not the entire period. I mean, y'all should memorize it anyways. It's
Yeah,
good.
you should memorize the entire periodic table if you're a chem major,
Okay, and in all honesty,
or if you're
right,
STEM major, my bad.
I don't know how many times it infuriated me where I had to like go back to the page, look at the periodic table and then like flip back to the front. Then I just forgot the mass I was looking at, so just memorize it. and I just
Rip it out.
Wait, you haven't memorized the masses?
I have the masses memorized of like common elements.
Yeah, me too.
Oh, what's chlorine?
35.45. Can you, he was talking to me.
What's chlorine?
Oh, I don't know, like nobody.
18, right?
Isn't fluorine 18 or 19?
999.
Yeah, it's 18.999.
Okay, I don't have all of them memorized. I've. some of the
That's
important
cool,
ones.
that's cool. Well, what's the answer to this question then?
I know I have to
I
look.
got C.
E.
All right, there's some Cs and there's some Es.
And I heard some Gs in there too, so I'm kind of confused.
E, elephant.
Wait, order.
E as in epsilon.
You know, what's the, yeah, because of our.
Yeah, but argon, remember, ionization energy isn't electronegativity. Noble gases still have ionization energy.
Yeah, but isn't it already satisfied, so it's gonna be better to remove it. To remove
No,
one?
but
She's supporting, she's saying that he's right answer, right?
Huh, wait, it's wrong?
so noble gases besides xenon do not have electronegativity,
Noble gases don't have electron-
but they don't have, but they do have ionization energy.
Oh,
Because you can still, think about it, you can still remove electrons from a noble gas.
It's just extremely energy constant. No, because I thought I heard him say something else.
Oh.
I said E.
Okay, again, so the answer in this case is E. Yeah.
Wait, it says order, is that from like smallest to biggest or biggest to smallest?
Well,
I assumed,
I'm just looking at the greater than signs.
oh,
It's gonna point to the biggest thing, right? Or not
oh,
point it.
yeah, well, yeah,
But-
that makes sense. I just thought it was like, I was going from the smallest to the biggest energies, and so I chose C since it's going from the smallest to the biggest.
Yeah, so like, you know what they say, the alligator likes to eat the biggest thing, so,
What is it supposed to be?
it's an alligator, so they always open their mouth to the biggest. They always open their mouth to the bigger thing, right? So like bigger because they're hungry, right?
Well, that's some genetic crossing.
No, yeah, no, I get it. I just thought like it was like the arrows. Like I didn't even think of them as like the greater than signs. I just thought they were just like arrows. I appreciate the artistic
Can you put a
image.
$5?
No, that's an alligator with a tongue. Okay, so
That's that genetic cross. between a duck and an
Permutations.
okay. All right, number 38. First ionization energy of the element blanks. This is just the trend, seeing if y'all remember the trend of ionization energy. And if you remember the trend of atomic radius, then you pretty much know the trend of everything else. Yeah.
Well, I answered. the
Wait, are you going
question
to
already.
health groups?
Yeah.
And you have to show everyone that you're a top scholar?
Yeah,
Pictures are all over our school.
I have to go promote
They
the
don't have a-
program.
They have a golf team though.
That would be the kid.
Okay, bye guys, thank you for the session.
Yeah,
It was great.
thank you for showing up. Cool, come on. Okay, Homer, what's the answer?
A.
Do you all agree with him? He said A for the people on Zoom.
Yeah, I agree with you.
Alex, what do you think? Jake, what do you think? Ashley, what do you think?
I agree.
Awesome, thank you very much. And he agrees as well. And then Jake is good. Okay. So A, yes. Perfect. If there's no questions, I'll go ahead and move on. This will test you on if you,
Real quick, just to double check, did you say that number 35 was A after all? Oh, D, okay.
yeah, because that's corresponding to argon. Like
So number 35 is D or 36 was D?
36 is D, 35 is A.
Oh, okay, thank you.
Okay,
I just wanted to confirm something too. I'm sorry. So for ionization energy, we're saying that it increases from left to right and then from bottom to the top.
yeah,
But then it's the opposite for the radius.
yeah, so like I said, if you know the atomic radius trend, all the other trends you're gonna learn in this class are opposite to that.
Oh, okay.
So as atomic radius increases left to right, you're actually, or as atomic radius decreases from left to right, you're increasing ionization energy. And as atomic radius increases from top down, you're gonna decrease ionization energy. So they're inverse relationships.
Okay, thank you, got it.
It'll make a lot of sense too if you know the trend for electronegativity, because it's larger for, or it's harder for a larger atom to attract more electrons. That pulling, like, it doesn't have that much of a pulling power.
Exactly. It can't pull. It's not like no, I'm just kidding. Okay. What's the? Okay. The lowest first ionization energy, so we're looking for something to the left, because we're talking about groups, we want something to the left, right? So again, alkaline metals is group 1, and then alkaline earth metals is always group 2. So, and we know halogens are pretty over there to the right. Transition elements are in the middle. Noble gases would not even come close to being the answer, right? We know those are always gonna have very high ionization. So yes, the answer is D.
What does the first ionization energies mean? Like, why does it say like first?
Yeah, so the first ionization energy is the amount of energy to remove the first electron. So,
Okay.
so like sodium gas going to sodium plus gas. And then plus an electron. That's the first ionization energy. The second ionization energy is if you take that product and then you ionize it one more time to make sodium 2+. And this is very energy. This is going to be a high ionization energy because sodium doesn't want us to lose a second electron, which is why we always see sodium with only a +1 charge. It costs too much energy it takes too much energy to remove that second electron as we did here.
Oh, okay, got it. Thank you.
40 is, you said D. Well, yeah. Okay. So what are we thinking about 40? Because I didn't answer her. She was asking a different. It's always helpful to remember that if you lose an electron, the first ionization energy, and you end up with noble gas configuration, that second electron that you try to remove is going to have a super high ionization energy, because once it obtains noble gas configuration, it's extremely happy. The atom is extreme, or the ion is extremely happy because it has a full outer valence shell. And it doesn't want to lose any more. So removing a second one would be extremely hard to do. So think of which ones after one ionization energy become noble gas configuration. Anyone on Zoom have an answer?
So you don't know. No, all I know is that the experience is things.
Let's see if I can copy and paste this figure out table now. Copy. Wait,
Probably she had.
one more. Okay. It's kind of small, but I'll zoom in once we start talking about it. Okay, anyone have an answer on Zoom? Y'all already say something? I didn't. Yeah, Jake said good last time, okay. Anyone? Okay. So if you're not sure, you have to take 2 electrons from each one, right? Or let's first take the first electron out of each one. Let's do phosphorus. We'll do that in blue. When phosphorus loses 1 electron, right now it has a 3p3 electron configuration in that region right there. Right here. But once you lose that first electron, it actually has this configuration, right? It has the same configuration that silicon has, which is not noble gas configuration, right? Now for something like aluminum, let's see what we have. aluminum is right here. So right now it would have that 3p1 configuration. So if you remove that electron, then you end up in this position. I'm not saying that it's magnesium, I'm saying it has the same electron configuration as magnesium. Magnesium, on the other hand, let's use purple. Magnesium is normally right here, right? But once you lose that electron, you have sodium configuration. And then sodium is all the way over here. So that's 2 more. So sodium we'll do in red. Sodium is normally right here, but once you lose that, it has the same configuration as neon. Once you lose the first electron, right? And then lastly, silicon. So we'll do orange. Yeah, so silicon's normally right here. Once you take the first electron away, it's gonna have aluminum configuration, right? So right now, we've only taken 1 electron from each element. But which one right now would be the most stable based on the highlighted regions?
Sodium.
Sodium, right? Because it has noble gas configuration. So you think it's gonna be easier or harder to remove the second electron from sodium?
Harder.
Harder, right? So that's why sodium would have the highest second ionization energy. All right, does that make sense to everyone? Okay, perfect. I think, I mean, no one said anything, but I just assume y'all are fine. Good talk. Okay,
So I have a quick question.
yeah.
So for silicon, if you take 1 electron, it's like aluminum, but if you take 2 electrons from silicon, would it be magnesium?
It's not, it's gonna
Not
have the
the
same,
magnesium, but like configuration.
it would, yeah, it would have the same configuration as magnesium.
Okay, gotcha. Thank you.
See, silicon.
Rich,
Silicone.
it's silicone, bro.
Silicone's an
He changed the
entirely,
way he said it.
silicone's
He
an
said
entirely
silicone.
different thing.
He said it really weird this morning. I don't remember what he said.
Okay, what is the, let's do 41 and then we'll call it wraps for this week. And we'll continue next week. What is the second ionization energy of calcium? Is that true?
Is it?
Tomer's shaking his head and disagreeing.
No.
Disagreement.
It might be A, it might not be.
It could also be B, C, D, or E. So, Kristen, you want to tell me what you got? And don't go with what everyone in class said. You don't have to be a follower.
Well, if I'm being completely honest, I haven't looked at it too much, but I can talk you through my thought process if that's okay.
Go ahead. Let's hear
Okay,
it.
cool. So calcium, if you take away 1 electron, it would be potassium. If you take away 2 electrons, it would be argon. So
It's not
Good.
it's not potassium or argon. It has the same configuration as them, right?
yes, it's the same configuration. It's just easier to say that
Okay, yeah.
versus saying configuration of argon,
Yeah, yeah.
So it would have what? Damn, okay. Would it be plus?
So remember,
Plus
the second, like for sodium, it goes from sodium gas to sodium plus gas. That's the first ionization. So
Yeah,
that's-
okay, so then it'd be calcium 2 plus
So it'd be,
for taking away 2.
oh, remember, it's only, you only take 1 electron at a time. So
Oh,
calcium
right.
going to the second one. So it would have to be, it would have to have lost 1 already, right? So calcium.
Oh, true.
Going to calcium 2 plus would be the second ionization energy. Because remember, you're losing them 1 at a time. It's not always happening. Even though we say calcium is 2 plus, it's always going to happen 1 at a time.
Oh, okay, that makes sense. Well then,
Right after each other, but you always write it as 2 reactions. So. So
okay,
like for
good to know. Good to know.
So for like the first ionization energy for sodium, it would go from sodium to sodium plus. And then the second ionization energy for sodium, it would go from sodium plus to sodium 2 plus. Which is just an example, but this is highly unfavored reaction, which is why it probably wouldn't happen. Any questions on that?
No. So the answer in this case would be E, right? Because it's going from the CA plus to CA2 plus.
Well, which side should the electron be on if we're losing the electron?
Oh, I see. It probably then A.
Correct, yes.
Okay.
Does that make sense though?
Yeah, that does.
Okay, perfect. All right, that will be, let me go ahead before I release y'all. The bell doesn't release y'all, I do. Just kidding, I'm just kidding. Please sign in, make sure you leave your social security number in the feedback box,
And your credit card information.
credit card
and
information,
Your address.
not the address, I don't need that.
I need it
Oh,
for personal research.
just kidding, guys, just kidding, we're kidding.
Are
We
we?
should, we should probably cut that out though. But yeah, y'all are free to go, once y'all do this, please do this because we always, like Maria, she comes to our sessions all the time. But when we look back at
I was
this,
pulling out my phone right now.
but when we look back at the data, it shows up that she only comes to our sessions 2 times in a span of like 3 weeks, which is obviously not true because she's here every day. So Maria, do us a solid.
I'm doing it.
Thank you.
I keep spelling.
And y'all are already here anyways, but please come to our Monday one at 2:30. It'll be worth it. Probably doing some of more of these problems, probably some of the structures, who knows?
Yeah.
Yeah.
Oh, Lewis Dodge.
Remember, I just call them Lewis structures.
We're gonna be drawing some molecules. Start memorizing everything. Just start memorizing this little table. Yeah.
Oh, yeah. Memorize the geometry.
That's good.
Yeah.
No, I never memorized those. I went through all of Chem pre AP and AP without memorizing those.
Well, now you gotta memorize them.
No,
College
I'm
Chem.
not going to.
What did you get on the AP exam?
Should I?
Oh, I took chemistry online. No, I got a 4. I got a 5.
Here is your about. Okay.
But I took chemistry online.
You should start memorizing this table if you can. I promise it'll only help you. But yeah.
I'm going to.
All right.
Could you show the QR code one more time, please?
Yes.
Pass my phone's about to die.
Thank you.
Then this one only undergoes SH one.
No, I don't.
Oh, do you
Oh,
want to do that?
That's one only no beta.
All right, have a good weekend, everyone. Whoever left on.
100%.
Bye, y'all. Thanks.
No, all right, thanks, thanks.
Have a good one.